So on to question 14. So this is the first of the in-amp questions, meaning instrumentation amplifier. So all of the instrumentation amplifier questions I think use the 2 op amp in-amp structure, which is what we used in our biopotential amplifier system that we built. So here we've got question 14. Let's just put in the values here. So R1 is 20 kilo ohms, and R1 appears twice in the circuit, of course. R2 is 5 kilo ohms. So the operation of this in-amp here, in order to do its job very effectively, you need to have very carefully matched resistor values. So these two resistors should be very, very close to being equal, and these two should be very close to being equal. And if you don't achieve good resistor matching, then the performance of the in-amp is going to be degraded. So you start getting common mode signal leaking through to the output here, which will really degrade the performance of it, especially in a biopotential amplifying application. So the basic idea is here that the differential input signal to this amplifier is V2 minus V1, and the output in an ideal world would be just proportional to V2 minus V1, and it wouldn't be affected at all by the common mode input, which is the average of V2 and V1. So what we're asked to calculate here is the output voltage. For this one you're asked to calculate the differential mode voltage gain of this in-amp. So actually we derived that in a previous lecture. So all it is it's going to be determined by R1 and R2. And so A diff is normally the way I write the differential mode gain for an amplifier, and it's going to be equal to, in this case it's R1 plus R2 over R2. So just note that unlike the previous non-inverting op-amp questions here, I've just got R1 and R2. Those labels are the other way around than what they were in the previous examples, just because they're done here kind of like a mirror image between these two match and these two match. So I ended up with R1 and R2 the other way around here. So hence it's R1 plus R2 over R2. So that's the differential mode gain of this in-amp here. I suppose I'll calculate that first, just get out the numerical answer anyway. It's going to be 5 plus 20 divided by 5, which is just equal to 5. So that is the differential mode gain there, it's 5. Just to remind you what the output of an in-amp like this would be, it'd be Vref. Now in this case Vref is equal to 0. So the reference voltage at the bottom here is 0, so that term is just going to be nothing. That's going to be a 0. Plus the common mode input voltage multiplied by the common mode gain, and then the differential mode voltage input multiplied by the differential gain. So what you're hoping in an ideal world, and this is an ideal circuit where you've got ideal op amps and you've got perfectly matched resistors, the common mode gain is going to be 0, which means that this whole term goes away, and the entire output of the amplifier just depends on the differential input voltage. Just to remind you what VCM and VDiff are. VCM would be the average of V2 and V1. So this is what we call the common mode input. V1 plus V2 over 2. That's what VCM is. Now this generally is, in biopotential measurement, is like a voltage that you don't want and you're trying to get rid of, because it consists of a lot of 50 hertz interference and so on. What you're actually trying to amplify is VDiff. So this is the difference in voltage between two electrodes. So this would be V2 minus V1, and this is what you're really interested in getting. So that's VDiff. So this is the good stuff here, and that's what you're trying to amplify. This is horrible and you're trying to get rid of it. So you try and make sure that you design your amplifier to have very low value for ACM and then you have often like a nice big value for a diff. Now I'm not sure why that label is popped up over the. Right, there we go. So you're trying to have a higher value for a diff. Now in this case we've just got a gain of 5 for a diff. So put that in here. 5 is what you're asked for. In this case, that's just the gain. The units of gain, like sometimes you'll see them written down as volts per volt if it's voltage gain, which is what we're looking at here. So it's essentially like a dimensionless quantity. It's a ratio of two things that have the same units or the same dimension. So in this case, no units are specified, and we just type in the number. Okay, question 15. So what are we looking at here? We got V2 is 0.7. V1 is 1.1. Now the resistor values are R2 is 10k and R1 is 20k. So you're asked to calculate V out. So as I said before, the formula for this is basically V out is going to be equal to the reference voltage, which in this case isn't 0 anymore, right? So this is, as we had in our real circuit that we built, we had a fixed reference voltage which was higher than 0. In this case it's 2. I think in our circuit that we built, I think it was 1.66, but in this case it's 2. So the output is going to be Vref plus whatever amplified version of the input we get. So Vref plus, and we're assuming in this case that the resistors are perfectly matched. So R1 is the exact same here as it is here, and R2 is the same here and here. So the common mode gain is going to be 0. I'll just put it in here for a second, but it's going to disappear again straight away. Plus A diff times V diff. And as I wrote there a second ago, or a minute ago, VCM is just the average of the two inputs. And V diff is the difference between them, which is the signal we're really interested in. So this is the signal that we're trying to amplify. So the good news is that ACM, if you match your resistors perfectly, this bit just goes away, which is good news. And we're just left with Vref plus the differential gain times V diff. Now for this circuit, we derived an expression in class for A diff, and it was just R1 plus R2 divided by R2. So again, it's just determined by the relative sizes of these two resistors here. So V out is equal to Vref plus R1 plus R2 over R2 multiplied by V2 minus V1, which in this case Vref is 2 volts. R1 plus R2 over R2 is 20 plus 10 over 10. So the differential gain is 3. And V2 minus V1, that's 0.7 minus 1.1. So this is 2 plus 3 times minus 0.4. So 3 times minus 0.4 is minus 1.2. So this is 2 minus 1.2, which is 0.8 volts. And that is our output. Okay, question 16. Now in question 16 we're looking at slightly more realistic circuit in some ways, in that it's acknowledged here that the resistors may not be perfectly matched. So you can see that the values have been written into the circuit as OR1 and OR1 prime, and then OR2 and OR2 prime. So they're like probably supposed to be exactly equal, but of course they never end up being perfectly equal in a real circuit. So what you've been asked to calculate here is the common mode rejection ratio, or the CMRR. So this is one of the key figures of merit for a biopotential amplifier. You're looking for one. You're looking for a very high value of CMRR if possible. Like ideally, it'd be like over 100 decibels. All it is just the ratio of the differential gain to the common mode gain. So in a perfect world, the common mode gain would be 0, and then the differential gain could be whatever you need it to be. The problem is that when these resistor values aren't perfectly matched, then the common mode gain isn't quite 0. So the way that you calculate this is fairly simple actually. It's just CMRR is equal to, now it's really what it is it's the ratio of ADIF to ACM. So it's just ADIF divided by ACM. But in order to express it in decibels, it's going to be 20 log 10 ADIF over ACM. So it's the ratio of the two of these, and we get log to the base 10 of it. So decibels, if these were already power gains, then it would be 10 log 10 power gain over power gain. But because of these are voltage gains, they need to be squared in order to become power gains. So normally when you use decibels, you're comparing ratios of powers. So hence it's always 20 log 10 ADIF over ACM. So I have to do this in octave. So I've got 20 times log 10. Then I've got ADIF, which is 11.16, divided by ACM, which is 0.076. And the bad news is that that is giving me a CMRR of 43.337. And that is in decibels. Now I say the bad news because that's just a woeful CMRR value, so that wouldn't perform very well as a biopotential amplifier at all. You'd want to be at least doubling that really to get into respectable territory. But anyway, that is the answer to this question. So 43.337. So again, you're asked for the answer in decibels, but you just type in the number into the box. That's all you type in. So, question 17. So in this question, Vref is equal to 1.666 volts. I think that's actually the same as what we had in our circuit that we built. OR2 is 500 ohms and OR1 is 10k. So one thing we can say here straight away is we're going to have a much bigger differential gain than we had before. So ADIF is going to be OR1 plus OR2 over OR2. And that's going to be 500 plus 10,000 over 500, which is equal to 21. So the differential gain here is 21. So whatever the difference is between these two input voltages, that's going to get multiplied by 21, then added on to the reference voltage, and that's what we're going to get at the output here. So V out is going to be Vref plus that differential gain, ADIF, multiplied by V2 minus V1, the differential voltage input. So in this case, we know that V2 is 2.5 volts, and V1 is 2 volts. So Vref is 1.666, A diff is 21, and 21 is going to be multiplied by V2 minus V1, which is 2.5 minus 2, which is 0.5. So that's 1.666 plus 21 times 0.5, which is 1.666 plus 10.5. Now you can already see that we're into, this number is way higher than the 5 volt limit of what this op amp is going to be able to produce. So it's being powered from a bipolar supply of 5 and minus 5. So the highest voltage that this could possibly get to is going to be 5 volts, and we're already way over that here, because it's going to be 10.5 plus this is going to end up higher than 12 volts. So what this means is, that's positive saturation. Hence, the output voltage is actually going to be equal to 5 volts, because that's where this op amp is going to saturate, at 5 volts. So this, once you discover that the output voltage that you would be getting is outside of this range here, all this maths becomes bogus, because the initial assumptions aren't going to be fulfilled anymore once the op amp can't get up to the voltage that you would need to get to. So basically, once you see an answer coming out that's higher than 5 or lower than minus 5, if those are your supply voltages, then you know you're into saturation, and then all you're actually going to get at the output is the saturation voltage. So 5 volts in this case. Okay, question 18. So what have we got this time? V2 is 1.3 volts. V1 is 1.1 volts. And we can see here R2 is 1 kilo ohm and R1 is 5 kilo ohms. So I can see straight away that the differential gain here is 6. So it's 1 plus 5 over 1, which is 6. So A diff equals 1 plus 5 over 1, which is 6. So that's the amount by which V2 minus V1, our differential input voltage, gets multiplied by 6 to come out at the output here. However, there is also a reference voltage down here, so the actual output voltage is going to be Vref plus that gain multiplied by V2 minus V1. Now again, I've left out the term here for the common mode gain, because we're assuming this is an ideal circuit. These resistors are perfectly matched and these are ideal op amps. So the common mode gain is going to be 0. So I only need to worry about the reference voltage and the differential gain. So Vref in this case is 2 volts. A diff is 6. V2 is 1.3 and V1 is 1.1. So that's 2 plus 6 times 0.2, which is 2 plus 1.2, which is equal to 3.2 volts. And that's fine, that's well within our voltage supply range here. So in this case, the op amps are powered from a single supply, 5 volts and 0 volts. So 3.2 is comfortably within that. So that's going to be our output voltage.